Hello everyone. In this video we're going to look at the data for a two-factor ANOVA where we have two separate independent variables. One is gender, the other is drug, and we're looking at memory scores on a test in an elderly population. So we're going to start by labeling our variables. Right now gender just has 1s and 2s in this column, and we want to change that to male and female. It'll just make the output easier to interpret. To do that, I'm going to double click on the gender variable, and I'm changing variable 1 to male and variable 2 to female. Okay. Then I'm going to close that up, and then I'm going to do the same thing for drug. I have drug A and B currently labeled as 1 and 2. So I'm going to double click on that and change 1 and 2 to A and B respectively. Okay. Now my dependent measure there is memory amongst the elderly. So to run an ANOVA, I'm going to click on ANOVA and then click on ANOVA again. And then to run this ANOVA, I'm going to put my dependent variable, memory scores, into the dependent variable box. And then I'm going to move my other two variables into the fixed factor box. Those are my two independent variables, gender and drug. You can see that it gives us an overall ANOVA summary table there. I'm also going to ask for omega squared and eta squared as well for measures of effect size by clicking on the boxes there. So we have three effects we're testing for. We're testing for the main effect of gender, the main effect of drug, and the gender by drug interaction. Okay? And we're going to interpret these based on the p-values and effect sizes. So we're going to start by looking at the gender by drug interaction. Right, so our gender by drug interaction has an F of 4.74 with a P of 0.03, which has, moderate evidence against the null hypothesis that we're looking at there. Now, what that means is that the effect of drug depends on gender. So the drug has different effects for males and females, but we need to explore that by looking at simple effects. So to look at the simple effects, what we're going to do is start by looking at estimated marginal means. And I'm going to move gender and drug in at the same time into the same term, so it'll look at the interaction term for us. And it automatically will give us a plot. I'm also going to ask for the marginal means table. But we can see here that we can look at males with drug A and drug B, and females with drug A and drug B. And you can see that males have higher scores on drug A than drug B. Females also have higher scores on drug A than drug B, but you'll note that the difference is bigger with males than females. So we're going to look at simple effects to explore this, but this is basically a definition of an interaction, is that the effect of drug A versus B depends on whether you are male or female. Here it looks like males did quite a bit better with drug A than drug B, whereas females maybe did a little bit better with drug A than drug B. So to explore this, we're doing simple effects by clicking on the post hoc test menu and then selecting gender by drug interaction and moving it to the box on the right. We are not using a correction, so we're going to click on no correction, and we're also going to compute Cohen's d with confidence intervals around d. So if I'm looking at the simple effect for males, what that means is for males, I want to compare males with drug A and males with drug B. The difference for males between drug A and drug B was 3.64, right? So that difference between drug A and drug B for males is 3.64. The p-value for that comparison is 0.0003, which tells us that difference is unlikely to be due to sampling error. And Cohen's d is 0.96, which tells us that it's a large effect. You'll notice here that our confidence interval ranges between medium 0.44 and 1.49, which is quite large. Okay? And you're often going to see this at large, wide confidence intervals because our sample size is fairly small. So if you want more precise estimates of that confidence interval or of the population parameter, you need a larger sample size. Now I could also look at the simple effect for females. So for females, I'm comparing these two means for drug A and drug B. And here I find a difference of only 0.63 for females, and the p is 0.52, which tells us that the difference for females was probably just due to sampling error. The d is 0.17, which is a small effect. And then the confidence interval, we're 95% sure that the true value for the D ranges somewhere between negative 0.3448 and 0.6789. Okay, so what this means in terms of interpreting this post hoc test is that for males, they did quite a bit better with drug A than drug B. For females, both drugs were equally effective. Okay, so that is our interaction. Next, we're going to go back and look at the main effect of gender. So overall, is there a main effect of gender when we ignore which drug they're taking? And here we get a P of 0.11, which is data that's, pretty weak evidence against the null hypothesis. We can look at the marginal means to see which group appears to be higher. By looking at gender here under marginal means, I'm going to add a new term and just look at gender. So when I look at gender here, you can see that females tended to have slightly higher scores on the memory test than males. But note that that's not a terribly interesting finding because this main effect was qualified by the interaction. Right? It really depended on which drug they were taking. That overall, males did better with A than B, whereas females did equally well with both of them. Right? Here, this main effect is not terribly interesting, and it's also kind of marginal. It's only a P of 0.1, which suggests that the difference is probably just due to sampling error, right? Or it's very weak evidence against the null. Okay, our next effect we're going to look at is the main effect of drug. So look at the main effect of drug. I'm looking at the data on the drug line. I have a P of 0.002. And for drug, what I'm going to do is go back to my add a new term under estimated marginal means and just look at drug. So the main effect of drug has a very low p-value, which means that the difference we're observing is probably not due to sampling error. And in fact, people overall did better with drug A than drug B when you ignore gender. But notice how misleading that is to say that, well, people did better with drug A than drug B. That's really not true, right? So overall, on average, people did better with drug A than drug B, but gender is very important. Males did a lot better with drug A than drug B. Females did not. There was very little difference between them. Now, the last bit of information you need when summarizing the data for a factorial ANOVA is to get the standard deviations for the means. You'll notice that jamovi here gives us standard errors rather than standard deviations. You can convert the standard error into a standard deviation by multiplying it by the square root of n, or you can just go to the exploration menu and click on descriptives. And then what we're going to do is move our dependent variable into the variables box and move gender and drug into the split by box. And here it'll give us the means and the standard deviations for all 4 cells in our design. Find that you can also look at the main effects, means and standard deviations, by only looking at one variable at a time. So here I'm splitting just by drug, and you can see that I have drug A and B means and standard deviation. Or alternatively, I can move gender over and get the means and standard deviations for just overall males and females. So those are useful when you're looking at the marginal means. All right, so that is all you need to do, or need to know anyway, to run the analyses in jamovi. So good luck with your 2-factor ANOVA.